past, they are no longer infected. Then now they become what? Become recovered. This model assumes that once you recover, you don't get infected. That's why it is very, very limited. And I've said you'll find that in R, but the only particular diseases which it is able to model, and we are told by a specialist that it can model what? Smallpox, any other? Measles.
What about the current disease? What about the current disease which is threatening Kenya?
Which one?
Because it's unusual.
I want these people to tell me. Maybe I'm a mathematician. If you don't tell me, that's what I'm asking them.
Oh, yeah. I'm interested in that.
Can it? The mpox. Can it model mpox? Yes, I have. Yes. It can. So once you recover, you cannot be infected again. You can't.
You get it is a DNA virus, and the DNA virus are quite stable.
Yeah.
So the risks of it mutating is very low. It's very low.
So there's high chance that you cannot be infected again.
So there is no infection.
Yeah, and that's why you cannot do modeling if you don't collaborate with the what? The expert in the area. You'll be having a useless model. So from that knowledge, we can therefore comfortably use an XIR model to model mpox, right? We have said you can't do it in malaria, you can't do it in HIV, and others. So you should be able to know that HIV is SI, because there's no recovery. Either you are susceptible or infected, full stop. No recovery, right? Now, assuming we are now modeling mpox by this model, and the model is presented the way it is. What have you assumed? We have this model in R. If you run it, you get your graphs, right? But what have you assumed? We were told that this model is assuming that there are no deaths and there are no births, right?
Also migration.
There is no migration, which therefore means that if you use this model, even to model mpox or smallpox, then your model is likely to be useless. If you test it with real data, they won't agree, right? So we can modify the model. From here to moving very fast. So you can modify the model by introducing what? The births and the deaths, right? So we can change this model to have the births, then minus BSA, then we have the deaths. Now, there are two types of death rates. If you're dealing with malaria, if you're dealing with the smallpox kills, right? As a disease, it kills. So we have two types of death rates. We have the natural death rate here. Let's give it DN, the natural death rate of susceptibles. How did you arrive at the natural death rate? She doesn't have an economist or a who. How do you arrive at the natural, how do you get the natural death rate? Or what is the natural death rate? How do they define it? How do they come out with it? Now, we also have the infected, if this disease kills, then we have the natural death rate minus the death rate due to the disease. This is natural. This is death rate from the disease. Right? And again here we have the natural death rate. Remember, we have improved this model by adding the births and the what? The deaths. I want us to understand, how do you get the natural death rate?
I think the number of people dying per 1,000 in national.
So how do you make the difference between the natural death rate and the death rate due to the disease? That is very important in modeling. Otherwise, your model might just be correct, but your parameters are wrong. So you're getting a wrong, not because the model is wrong, but because your parameters are wrong.
Professor, actually I think the national death rate will include even the death rate due to the disease.
Yes. The national
death rate.
Yes.
So it's total death rate?
National.
Yes.
Total death rate of a country or in the country all over the population. Because you get the total all the deaths that have occurred and you get the total population of the country. Maybe if you divide, I think it will give something like national.
Natural.
Oh, natural.
Natural death rate.
Natural death.
Yes.
That one is not death rate.
Start defining what is natural death.
So that's how the Kenyan Bureau of Statistics defines it and how it is calculated. Because we have the malaria deaths, right? We have the HIV deaths. Then we have the natural death rate. So what is natural death rate?
So that is a death that is not associated with the disease in this ratio.
Exactly. It is, you know, nobody can live forever. Even if there's you're not infected by malaria, by whatever, eventually you will die. So the best way to do the natural death rate is to determine the lifespan of the people in a given country. So what's the lifespan in Kenya today? 67. So you take 1 out of 67, then you find the natural death rate in Kenya. It might differ from county to county. Check that from the statistics, the Kenya Bureau study. So that gives the natural what? Death rate. I'm saying that your model might be correct, but your parameters are wrong. So when if now you simulate it against the existing data on the ground, they will not correlate, simply because of the parameter. That's why I challenge them that we need to determine this parameter, because you don't have them. If you look at my work, I'll just try to approximate them, because you don't have them, and you don't have the capacity to do that, but you people in the research institute, you have the capacity to do them, so that if I'm able to get these parameters correctly, then I'll simply be working on my model to ensure that it corresponds to reality. Yes.
For the purpose of the model then, is it okay for us to assume, because first of all, how are we now, according to the model, defining natural death?
So,
because my question is, would it be safe to assume or make an assumption that in our case, natural death then will be all other deaths other than death being caused by malaria? All others other than those being caused by malaria for our application will be natural death.
So when eventually when you do your model, there must be a table where you're defining each and every parameter and where you have obtained it from, right? That's when now we can understand your model, so that somebody else doing the same thing is able to find the same result. So you define your parameter. Natural death rate is the death rate from every other thing apart from malaria. But remember, you may not find that death rate So sometimes we just use the natural death rate as a fraction of the reciprocal of the lifespan of people in the camp. But you must define it so that it becomes clearer to the person reading your what? Your work. Right? But now, so we have improved our model. Now, is there any disease that we can model using an SIR without births and deaths? Is there any?
Where people recover.
Genetic.
But how do you
But do they kill, are they not killing them? I mean, do they recover? Yes.
I think flu.
Use the mic.
Use the mic.
Let them use the mic.
For those who want to make comments.
Okay.
You can have another mic going
There's
around.
another mic.
Where's the other mic? Because you know, I want to get this from the experts. So that as a mathematician, I don't want to do my own things.
There are genetical diseases like sickle cell anemia, where somebody is born with it. They may not, with good management, they may live up to maybe even to 30 years. But in most cases, if they don't get good management,
But can the disease kill them?
yes.
If it can't, then this model cannot work. Yeah, it can't. This can only work if the disease does not kill them. Maybe a classic example of using this model, the only model may be common cold, which takes about, like now when students report to college or to schools, then one of them comes with common cold, then after 1 month, it is over within that period or within that school. Among the students, there are no births and no what? No deaths. So if you're modeling common cold in a closed environment and you're using this model, then you are going in the right direction. Otherwise, you'll find yourself not doing very good, right? Again, I want to challenge our students because Teddy, remember yesterday what I was telling you? We may ask you some very difficult questions, which you should be ready to. Yes. Now, so this is the way you can improve this, and you can improve it further. You can decide to have a migration and a migration, because like malaria, there's something called stability in disease modeling, or just modeling in general. So in disease modeling, we have the disease-free equilibrium, where there is no disease in the population, right? We call that an equilibrium, which looks like this. Yes.
Can I ask a question?
You can.
Now,
From my understanding,
Yes.
and I don't know when I'm correct to interpreting it like this, from equation 1, the number of those who are susceptible is reducing to recovery, to infected at a rate of beta.
Yes.
In equation number 2, the number of those who are infected is reducing by a factor gamma as they recover.
Yes.
Now, why
You're also reducing by deaths.
Yes,
And disease and death.
now my interest is on gamma and the beta because my question was going to be now, how do you determine them?
Determine the gamma and the beta.
Yes, are they values?
Now, I'm saying we are now going to modeling from here. So a person is susceptible. Now once infected, then it now comes to this class. Now this gamma here is the rate at which the person is recovering, which is very tricky because somebody might recover naturally due to the immune system and functions. How long does it take? For example, if handling malaria, how long does it take to recover? Naturally. How long? Or to die? Yes.
So maybe to put my question plainly, if for example beta would be a value 0.7,
Exactly.
the gamma would be 0.2, how do you determine?
That's what I'm asking. Because if you know how long it takes to recover, that can be a way of determining the parameter. You want to?
Yeah, I for a disease like COVID, they were saying it would take natural recovery would take around 14 days.
Yes.
So to get that gamma, it should be 1/14.
Exactly. That's why I was asking how long it takes to recover, so that your gamma will be 1 over.
1 over the period of
the period, natural recovery.
Now that will be about 3 weeks. So that will be 1 over 21. 21, that will be recovery rate. Gamma for malaria, right?
That would be the same for gamma?
For
gamma.
No, that is gamma recovery.
That is gamma for COVID.
And the beta
for COVID.
For a COVID model. Remember, this is not a COVID model.
I'm saying beta and the gamma. Even the beta would be 1 over something.
No. Beta is the probability. Remember, I can decide to add something here. We are saying that an interaction between a susceptible and infected could lead to an infection. So if you're handling malaria, if you're bitten by an infected mosquito, what is the probability that you will be infected? Where do you get that from?
I'm saying,
This from research.
no, you can either be infected and get the disease or you could not.
What is the probability? Because the probability could be 0.00001. Let's give an example for HIV/AIDS. An interaction between an infected person and a susceptible. Yes, what is the probability that the person is going to get the disease by first contact? It may not be 0.5. It's much lower, right? So that's what you have to determine.
So that
What is the probability? That is the beta by research. That's why I'm asking the source of 0.5, because you must cite where you get that from.
It depends. Are you using drugs?
Yes?
Are you using drugs?
For HIV. What for all diseases?
Malaria.
For malaria.
Are you on prophylaxis?
So I think that's why he's saying now that is for us to determine.
Exactly. I want that from you. I want that from
So the
you.
probability of you being cured
Yes.
if you're using drugs.
No. The probability of being infected if bitten by a mosquito.
It depends which mosquito.
It depends on which.
In malaria, there are some things that most of the people don't understand. And one of the issues is that the vector in that area, the vector in that area could be Anopheles, yes, but Arabiensis it doesn't love humans, but in fact it loves animals. So it will rather go for animals outside. It will bite outside and not inside. So most of the time it will bite animals. So it depends with what vector is around the area.
That's what gives the probability.
There are many things. That's just one of them. human behavior. It's another major issue that can influence
So remember, we can decide to add some factor here, which is called C, which is the number of contacts, right? So that beta becomes the probability of being infected by a single contact. If you're bitten once. But now, see now the number of contacts, or the number of times you are bitten in a given time period, right? So now there's also something else here, which is assumed. I want us to move to those things, the codes. Let me say something. You know the codes, once you're given a template, you can easily put in the codes from that template and simply run and find your results, right? But how do you make your model to correspond to reality? That is now the biggest test in developing a model. For R to accept it and put it in there, like you're using SBM, you're using all those others, right? Yeah. Now, this something being assumed here, which we are calling in modeling, we are calling it mass action. If you're doing a COVID model, you have to be very careful of that. This means that every infected person has an equal chance of mixing with a susceptible, which may not be the case if we are talking about quarantine. So how do we improve our model to handle a case where there is no quarantine, right? So you will come back to, you can modify this, we call this the force of infection. You can modify it to be beta, then we have S, then we have I over N, where I over N is the total, where N equal to S plus I plus R. N is the total population, right? So we are saying that only a fraction of the infected have a chance of interacting with the susceptible. So we are proving our model this way. So that if you're doing a COVID model and you're using this force of infection, then your model will go among the useless ones.
How about the opposite, exactly opposite of that? Because we have also cases where now this interaction between susceptible and infected is maximized. For example, in a classroom.
I'm asking the exact opposite of quarantine would be an infectious disease like TB in a cell, for example, among prisoners, or a classroom among small children. That is now where you completely have the opposite of quarantine. Quarantine, you see, you are limiting interaction between the two groups. These are the situations you are now maximizing the interaction between these two groups. How will that term look like?
Now that's what I was saying. That now you don't have I over A. Now we are using this one here. This is mass action, which means that all infectives have equal chance of interacting with the susceptible. Therefore, this formula here, this force of infection here will apply in a classroom situation. But apart from that, we'll use the other one. Where only a fraction of the infected can interact with the susceptibles, right? Yes, Alice.
I just wanted to insist so that we move.
Yes.
Beta and alpha are usually parameters, and those parameters are determined depending on the assumptions that you make during your modeling and the situation. So if there's quarantine, delta would be different from when there's no quarantine, like in that situation. So there are parameters that are usually determined
in a particular situation. I think we need to take it.
Thank you, Doc. So you know, when we develop this parameter, you'll be listing down the assumptions. If we don't have this one and this one, then the first thing you're assuming is you must indicate that there are no bugs and no depth. And then how logical is that assumption? If you're doing common cold in 2 weeks, that would be okay, right? But for malaria, that will not be accepted. We're also assuming here that we have mass what? Mass action. Every infected person has equal chance of interacting with the society. So if you have in a classroom situation or in like malaria, though may not be the case, but you have to give us the assumptions that what are you assuming, right? So that we don't judge you harshly. You must put the assumptions you're making in that model, right? But let there be logical assumptions. Because if they are useless, if they are obvious things and you assume they don't happen, then the model will not reflect the reality, and therefore the real data on the ground will be the same as what the model is giving you. So I wanted to make that introduction so that we can now go to run the models. And I'm saying run the model is not a problem, right? Yeah, but the problem is developing a model which is useful. So you can run this one. We can run the first one. This is inbuilt in our software, and you can add anything here as we have added. You can just take this model here, then add bn in the beginning at that point. You can add all of this into the same coding here, and it will run, right? Because this is inbuilt in R. So if you run it, can you try running it? So that you see the graphs. Yes? Why is that? Can you run it? It's canonical up, huh? Can it come down? Yeah. So we okay, good. So you are seeing the graphs. So if you run that model, and in this case we want all the graphs to appear separately. That coding enables all the graphs to appear separately, which sometimes may not be very good for comparison, right? I want to run the next one. The next one. So for that case, now please, because you are, remember, in coding the model, you have developed your model and you have coded it. Then these are the codes, and I've said if you modify it that way, you simply bring those parameters. For the SBT, you bring bn here, then minus dn minus dn. Di, you have a beta si minus gamma I minus dni minus ddi, right? Then you come to dr dt. Now in the return, in the list here, we'll have ds, di, and the R, only what is SIR, only. Then the proportion, now this is the proportion of the initial conditions where we are saying that susceptibles at 99%. And then we only have, this might not be correct. This means now this is correct, right?
Correct.
So those who are infected at 0.01 or 1%, and then at this point, at t equal to 0, nobody has recovered. Then what happens as time goes by? So we are now simulating. Then now we define our parameters here. We are saying that the probability of being infected is 0.3. There's 0.3 chance that you will be infected, which means we have 0.7 chance that you will not be infected. Then we are having gamma, we put gamma here to be 0.1. That is 1/10. For this imaginary disease, it takes 10 days, right? Then now, we are simulating from 0 to 200 days. If you're taking time in terms of days. Then now, this is now what solve the ODE, and then now this is now for the plotting of the results. And so we have said that if you do the plots, for that part, all of them appears in the same, in different graphs. If you run the next one, the parameters are the same, then are you getting that graph? So you have all of them in the same one. So this is good for analysis. You're able to see what happens with time, right? So that after about 50 days or thereabout, we have susceptibles. Are susceptibles increasing or decreasing? From that graph, they are decreasing, right? Where are they decreasing? They are getting infected. That's why they are decreasing. What happens to the infected? The infected increases to a given point, then reduces to 0. And then the recovered almost takes the day. So we have a small proportion of susceptibles, those who are never infected, and then majority has recovered, right? Now, in some cases, you'll find that these graphs, the graphs are, the margins between them is so big that it may not be very, very visible to see all the graphs within the same on the same graph, on the same y-x-axis, and you may want to hide maybe some graphs. As we have learned in R yesterday, we said that you simply do what? You just put a hash on the graph you don't want. If you run the next one, then the next one, if I don't want to see the infected, then just put a hash. You can see what the hash is in the coding. For my case, it's like 190, where the there is that behind the infected class. So you put a hash there, where we have the red color, you hide that, put a hash, you will not see the infected. If you put a hash under the recovered, you won't see recovered. I'm saying that's very important for visibility and clarity of your graphs. You may want to do that. Now, lastly, I want us to look now at a malaria model. And that malaria model is not in R. Remember, this was in what? In R. I had 3 things to do. I don't know whether we can move faster enough. Because I wanted us to develop our own model, which now you not find in R, then run it in R, then validate it. Let's get data from the real data, then compare with our model, then decide to reject it. But the good thing now, if you're a modeler, you do what? You modify it to correspond with real what? Real data, right? So this one here, so I gave a very simple one which we looked at Kipre, when we were there. I don't know whether you're able to understand it from the coding.
It's okay. The only problem is that the parameters have not been, they are many. I think that is what may confuse some of them.
Okay, so we can, let's try to write it down so that we understand the parameters. But if you understood this, once you have understood this one, then you can easily follow any model that without writing. Yes. Now this is now we have susceptible humans, right? Because we have susceptible humans and we also have susceptible vectors. No, the malaria, the mosquito can be susceptible and can also be infected, right? Yeah, you may be bitten by a mosquito which is not infected, so that will not give you malaria, right? So we have susceptible humans and susceptible vector, which is now the mosquito in this case. Then we have the exposed class of humans. If you are bitten by an infected malaria, then mosquito, sorry, then you become exposed, you don't become infected immediately. Is that true? You have very senior people. That's what I say. So you go to the exposed class, right? Then, from the exposed class, you can move to infected class. Then, from infected class, you can recover. Then, again, now, you can have a susceptible vector and also infected what? Vector. Now for your simulation to run, because we are using the birth rate of humans, which is a function of the total population, then you must have these 2 equations. This defines the total human population. This defines the total vector population. So that you can just simulate, you can just run the graph, a graph of NH against time to see what will be the total size of our population at the time you'll be doing your comparisons. Very important. in fact, to check the validity of your model, when we don't have the disease, then it should be very near to the population of the particular region you are handling. Like for example, if you're doing it for Kenya, what is the size of the population today? Around 55 million. So if you run this one, if you plot NH against time, starting maybe from some time back up to now, if you're doing it up to 2024, then you should be having about 55 million people. Then that now gives you the authority to use it to model our population maybe in the next 10 years, because it has been accurate in the past, right? But remember, there are changes in between. That also makes I decided to go for stochastic or deterministic. Now, let's go through the first one. The rate of change of susceptible humans with time is this one. This is the same as the first one. Then, you get malaria by an interaction between susceptible human and infected what? Vector, right? But then we are assuming that there is no mass action. Not everybody infected has equal chance of interacting with another with their susceptible. That's what we are assuming. So that we have I over N, right? Then plus M2 hat. Now this M2 is that because we have recovery, these are people who have recovered from malaria. So if you recover from malaria, then you go back to be, as I said. So M, there should be M2. So this M2 is like how long, the parameter is how long do you take to lose what? The immunity. Because once you recover from malaria, you may not get infection immediately. Is that true?
Yes.
6 months. So M2 will be 1 over 6 months, right? That's how you get M2. So you take some period before you become infected again. So these people here have recovered, so they go back to susceptible. Then of course we subtract those who have died naturally, right? Then you come to the exposed class. So this group now come to the exposed class. Then we subtract M1. M1 is the time somebody will take after getting exposed to be infected. Again, that you can tell us how long once somebody is bitten by an infected mosquito and he gets the disease, how long does it take to be? What's the difference between exposed and infected?
Exposed are not necessarily interacted with the victim. They are exposed, but infected have interacted with the victim.
But as soon as you are eaten and the mosquito transfers the parasite into you, then
you become infected.
Directly.
Yes, but it only takes time to process.
So if I have to refine my model, then I'll say that the exposed are people who already have the pathogen, but are not showing anyone.
No, so that would be wrong.
That's the wrong definition.
Exposed are people who have not interacted with the infected patient.
So the difference between exposed and susceptible?
For malaria,
Yes?
for malaria it may not apply.
For malaria? Let us do the experts first. For malaria?
You may not be able to differentiate susceptible and exposed. for the case of malaria because it almost means the same thing.
Which means that we can take the exposed to the susceptible class.
The problem in Kenya is that someone might have been exposed and is in the incubation phase. So at that period, is not going to be detected. So having that in our model will make it very hard for us. Because you are not going to know if this person is infected.
So it's very difficult to get MA.
Yes, because we depend them to be sick to come to the hospital. Unless you are telling me that you are going to do screening
For everyone in this place.
every day to the people, which is very
Which is not practical.
it's not correct.
So in that scenario, anyone will say something, can you? As you talk.
I wanted to take that route that Daktari has raised, that in definition of those terms, we define it in the compartments. We shall define it. Exposed can mean incubation stage. They have interacted, but the immune system is trying, I would say that, trying to fight it. So from exposed now, it will take, or alternatively, how long does it take for the first symptoms to start presenting themselves? So it will go into the definitions. I want to assume that if you're infected with, you're bitten by a mosquito, which is supposed to infect, then it will take some time for the symptoms to be now visible. So that can also be that time, because we expect that we don't do random testing for malaria. It's only those who are presenting themselves are the ones that will go to the hospital. So the period between being bitten and now you go to the hospital, you will fall under the exposed class.
So you give that definition.
Yes.
That the exposed class are people who are already bitten and already have the pathogen, but have not gone. But remember what you said, that it is extremely difficult to be able to tell who this exposed person is. And because of that, it might be much more intelligent to remove the exposed class if you are modeling malaria. So if you are modeling malaria, be careful if you have that class in your model. Because when you meet people from a research institute, you may not be able to defend your work. Okay. So assuming that they are as defined, right? The time it takes between the time the person is infected and the time he goes to the hospital. So that will be the exposed what? Exposed class. And you must put that in the definition of exposed, and you must also put it in the assumption that in your model you assume that the exposed class are people who already have the pathogen but have not gone to them or have not shown symptoms. If you don't do that, you will be skinned. So we have the exposed class. So now M1 now is the time they take before now they develop what? Symptoms. So that before they come to the infected, then they can also die naturally because they can't die of malaria. Then you come to the infected now, where this class comes here, then R also recover, then they die naturally, and this one is death by the disease. Then we have, then now we come now to the vectors class. The first class is the same, and once you do that, then now you can run the model. Can you run the model? I have about I have about 34 minutes. By 34 minutes it should be done. So you run that model. Now, this is why I was saying that it's very important to deactivate. Because remember, we have all these classes, 1, 2, 3, 4, 5, 6, 7, 8. What is clearly visible are only these three. So to see these ones here, you need to hide these two. Because there's a very big variation. It's like you want to use one scale to measure 1,010,000. It will be a problem. So if you disable these two, then you can see how these graphs look like. They may not be straight, but now because of the differences in the magnitude, we know what makes them straight, right? That's why I said it's very, very important to be recording. You know, if I want to see these graphs, I need to deactivate these two, so I see how they behave. And then so if you run the next chunk, so I've disabled all the rest, and I'm only left with the exposed and the infected. So this is the exposed, that is the infected. And I want to move to the last thing. So we have now the model validation. This is what I was saying, that once you have developed a model, then now you must validate it from data, actual data from the ground. So once you have that data, most likely it might take you back to your model, because if they're not agreeing, then you go back to your model. Check your parameters, check your model. If the two agree, all models are wrong, but a few are useful. That's the anthem of modeling. So you must ensure that your model is among the few that are useful. And that only happens if they are validated by reality. Remember I said, in modeling, you check the phenomenon, then see which mathematical formula corresponds to it, so that if you use that method, you'll be able to model the natural phenomenon. So if you want to validate an SIR model, so we have that. So what is important now is here. We have the empirical data, and then we have those who are infected. If you run that, so if you check in your coding, the rest of the thing just be basically the same. But now, this is the data we have collected from the ground, right? And then there is what your model is giving, right? So that if you run your model, then you end up with that graph. That graph gives you the empirical data which you have collected and then you have the model.
Where there was initial conditioning.
The initial of the
okay, there. Yes. So what I wanted to ask is, if today I knew the parameters, beta and the gamma for mpox that is going on in the country now, and I have collected some empirical data as indicated from line 334, and I fed in that this one I should be able to check if this model is going to apply to mpox.
Exactly. So when you do that and they compare the graphs, the two graphs, then that informs you whether you need to do something about the model, or you can use the model the way it is. We call that model validation. Because if the model is not validated, then you can't use it. Right? Yeah. Now, so this one here, if this were real data, then we can say that that model is not verified, right? Because this could be outliers from the collection of data. Therefore, this model not verified. This model can be used. We can rely on that model, right? Remember this one, an SIR model. You want to do for hours for malaria, yes.
So when you get the outcome, like we have gotten it,
Does the system, the model give you a leeway to adjust something? For example, if we wanted the red dots and the blue line to even close to each other more than what it is now, are we able to go back and modify anything in the model to bring them closer?
That really don't need to go back. Remember, if I want you to try this, change, let's start by the parameters. Assuming that we have the parameters from 0.3, I want you to make beta to be 0.01. 0.01. Gamma, let gamma remain the same. Then run that, see how the graphs will look like.
line what?
Line 325. Yours might be different. This one here. Let gamma be, instead of 0.3, we make a 0.01. Only that, then run it, see how the graphs will look like.
So instead of gamma?
Instead of gamma 0.3, make it 0.01. Which means that the probability of being infected is very small. Then how will the graph behave? Then I want us to go to something else on what he's asking.
Just attached to that. Prof.
Yes?
We make beta 0.01.
Yes.
When you do that, the root means the error.
There's a problem with your
And gamma remains 0.1.
everything remains the same.
So it changes a bit.
Change a bit.
But not very different from the previous.
Now, if you change gamma to maybe 0.7, yes.
And the beta?
Leave it at 0.01. Yes, run it.
0.7. Now the deviation is
is quite significant. So that's why if you use a wrong parameter, then you may think your model is wrong, but your model will just be right, all that you used a wrong what? A wrong parameter. Remember, this is something about intervention. From my end as a modeler, I will be able to advise that if you want to eliminate malaria, then first thing I look for the sensitive parameters. What are the sensitive parameters? Then I'll advise that if you can reduce this parameter to this one, then my graphs will be indicating that we have nobody infected. So like here, we have from our model, we have increased gamma, which is the rate of recovery or treatment rate, to 0.7. So if you can treat 70% of those who are sick, if our model is correct, then we can conclude that we are done with malaria in a very short time. If you can do that to everybody who is sick in the country. So that from my standpoint, I can advise that for my modeling, if you change this parameter, if you can reach this point, then we'll be done with malaria. And that's what's very important in modeling, mostly in applied. Yes?
Oh, I wanted just to find out on the same question.
Yes.
Are there some scientific discrimination techniques that someone can use so that we don't base it on the whoever is analyzing the data to make a conclusion whether the model is good or bad? We have discriminating techniques that can be applied.
Whether I get your question right, because remember we are one reason, the main reason why we are validating, before we give a recommendation, first we must validate the model.
What will make you decide whether the model is good? Is a good model or a bad one?
If validated.
The close fit between the empirical and the model.
Yes. That is what will make me decide that the model is good for use. You get the actual data from the ground, then compare the actual data with what you have. Before I make this conclusion, if this is my result, if this is the empirical, and this is what the model is giving me, I can't use that model to advise anybody. Yes?
If a model is validated,
yes,
the results become the same in material of whether
all data sets.
Whether the data is raw or transformed.
I think we need to process that data first before you use it here, to ensure that the data we are using, again, is not receiving us further. Yes?
My question is, assuming we have an outbreak, a disease that we have not heard of in the past, what we have done now on the board to adjust those values, beta, and see the changes in correlation of the model and what is on the ground. It then also means that what we observe on the ground, for example, a disease breaks out, it is killing people every day, no one is recovering. We can try to play around with those two values to get, using the data on the ground, to get a model that will predict the disease or something.
That's what we do.
Okay.
That's what we do. So that we are able to advise the policymakers that from my modeling, that's what was done during COVID.
Yeah, because I'm imagining like COVID, it never gave anyone time to determine the beta.
So I'll tell that from my modeling, I'm able to estimate from the way the disease is progressing, I'm able to estimate my beta and my gamma, and I'm able to give an advice from after a very short time that please, from what I'm saying from my modeling, if you're able to reduce this parameter by this %, then this disease is done. What the other reasons, other ways I don't want to go to, I'm leaving it to those students there We have the reproduction numbers, we have the bifurcation analysis, we have stability analysis. Like what I was trying to explain here, you know, we call this a disease-free equilibrium. There is no disease in the population, right? Now what happens if you disturb that equilibrium? Disturbing that equilibrium means what? You bring in somebody who is infected. So how will this equilibrium behave? Will it remain here? That depends on the reproduction number. It might remain here for some diseases, but not for COVID. Yes.
Just to add on what Michelle was asking, probably it will depend with the kind of, like you were saying, you have mentioned them, but I think you have not quoted them. One of the ways that we know that our model is okay probably begins from, before we start simulations, like the one we are doing there are things that we must do mathematically. Probably we must perform a phase plane analysis, whereby we will know how the disease will spread. And then we can also perform a stability analysis to know which are the stable points, which are the equilibrium points, and we test the equilibrium, the nature of the equilibrium points, whether they are stable, and at what point, at what causes the stability. Then we can also perform the bifurcation analysis. At some extent, we can also look at the sensitivity of the model. After doing that, then we can now come and do the simulation. Under simulation, we can either perform a data-driven simulation, where we use now data to simulate with that as we are doing validation the way it is. So we can do, we have the data present, and then we plot it alongside the outcomes of the model. Probably that one will tell us whether our model is right or not right. We can use those discriminations to know whether the model. But actually, at the beginning, before we do simulation, we can actually know whether the model that you are doing, you are modeling, the disease that you are modeling is actually okay, good, or not, after doing those particular mathematical analyses.
Yeah, to add on what you had given as an answer to the issue about if a disease is new. Yes. At times we use parameters from closely related diseases. For example, like COVID also, the parameters that were used, COVID presented itself like the SARS. So it was relative to what SARS was. So the values that we are having for SARS are the one that was used now for COVID for initial, to give a basis of the guidelines to take. And then as the disease progresses, now we are getting other values. I've forgotten that second statement.
That's like a startup,
yes.
Startup model.
Yes.
In terms of the numerical values, in terms of the parameters, right? But remember, even before you go to the parameter stage, there is this stability analysis, the sensitivity analysis, and that is very important to be able to tell that if you get a stable point, it is free or endemic, then what happens if you disturb the stable point? If you disturb a stable point, it can continue to be stable, or it may become unstable and stable, right? Yeah, but that's not for that is for us.
But then
Prof, I think it is still proper that once we have the empirical cover, we can still play around with the parameters as we look for the best fit. I don't see any mistake in doing that.
I think that's why I said I can still play about with the parameters and give advice by just playing about with the parameters, so that I can be able to, because there are some parameters which are not known, like the birth rate is known, so I don't touch that. But I can touch the interventions. What if we increase this treatment rate to this percentage? Can it help solve this problem. Because sometimes you end up treating 100%, but you are not still not solving the root problem. And then you can informate that even if you are giving treatment, this disease will not go away based just on playing about with what? The parameters. And maybe we need another method. Maybe we need to have a vaccine so that we have another model, another class of the vaccinated what? Class. Then play around with that class and be able to advise that for this disease, if you can have a vaccine, even at 20% efficacy level, will be somewhere, right? So from the model, and then just by playing around with the parameters, you are able to give some reasonable advice, right? But if the parameters have already been depicted, then the validity of the model will be based on the comparisons between the actual data, the actual result, and the model results, right? As I conclude, remember that was SIR, then we have now the malaria one. Validating the malaria model, which we developed. If you run and run the next one, that one, you need to interpret that, you need to reduce some. Now, so as I conclude, I wanted to say this. You will not find this model in R. This is what we developed. But you can change this model to fit what you are modeling. For example, currently we have a malaria vaccine. Do we have a malaria vaccine?
Yes.
We have it.
For children under 5 years.
For children under 5. Yeah, so that is an area that somebody can do a model and give an advice that this vaccine, what is the level of efficacy of that? It is no. 67%. Average 35%. Which is quite good. So that if this model, I can decide now that we have a vaccine, I'll not use the birth rate, and now use recruitment rate, because we're only doing it for those below 5 years. So how many get to 5 years?
We interrupted you when you were about to say something very important. That someone should be modeled. What about vaccine?
You have started saying something. You have started saying what should be modeled about the vaccine. You can pick that up again, please.
I was talking about the efficacy of the vaccine. And he's telling me that what we have is about 35%, right? So that in this malaria model, we add a parameter here, which we are calling maybe alpha times S, because we only vaccinate susceptibles, right? Then, now you add another class before exposed. You add the class of the vaccinated, right? So that, which therefore means, from this alpha, somebody now moves to vaccinated class, right? Then now we are able to simulate, draw our graphs of infected with time, and also vaccinated with time. Then we're able to see that how effective can this vaccine eliminate the malaria parasite in the community. If it does it, then you may advise that what levels of efficacy will eliminate them. Maybe at 35, it may not eliminate the pathogen, but If we increase it to 40, then perhaps we'll do away with that, with malaria. So we can give that advice that if you can just do a little bit research, just take this efficacy level to 40, you'll be done with the disease. And that is also a good advice you can give based on your modeling. Again, you may say that what happens if we decide to vaccinate everybody? If that is accepted, if that can work without a problem from the research centers, we can do that, then you can go that direction and see that if we do that, then how long will it take us to eliminate malaria from the community? And gentlemen, I want to stop at that point. Remember, you can just take this code the way it is, then add whatever you want to add on your modeling, then run it. Then you'll be able to get the result for your model. And I want to invite the MC, but I want to maybe some questions which you might handle briefly before we break for lunch. Then we come for some session in the afternoon before we end the workshop. I wanted to say something, but that's up my memory. Chair, questions? Yes, Chair.
Going back to the vaccine issue.
Yes.
If we were to go that direction,
yes,
do you think we can work with the general population or a cohort that has been vaccinated previously? Or we can start it by isolating a group, vaccinate that group, and then monitor all these other parameters to gather new data. So what I'm trying to ask is, will it call for new data, or we can just look for data that is already existing that has been gathered on course of administration of the vaccine?
If we have that data, we start from there, then we see this number of which you have vaccinated, what is the impact on the dynamics of the disease? Yeah. Yes.
We are interested in factoring in the impact of climate change on exposure or susceptibility. So where do we factor in that?
Now remember, I talked about geospatial models. I also spoke about genomic models. So you really have to know that where is the impact of climate. It is on the genome or just on the spread. If it is on the spread, then you can have a climate factor in the model and be able to see what is the impact of the changing climate. How will you measure it? The climate change. Changing temperature. So it affects what? It affects the force of infection, the biting rate. Then we bring it here so that we bring a factor here for the climate, so that at some levels, when that parameter, the climate, at some point, it increases the force of infection, so that the malaria parasite becomes more ferocious. Yes, so it spreads the malaria faster. So we can bring in that into this deterministic model, right? But remember, in the geospatial model, we use the same, just to predict the prevalence, even without going there, through GIS systems. So that at these levels of temperature and these other factors, we know that the prevalence will be this rate, so we can estimate, right? But now to get now the actual parameters to work with, we need now to go this direction. So now this is now application in a particular area. We also talked about the genomic models, where I talked about the backward distances. Because interventions changes the backward distances of the pathogen. So that also determines whether the pathogen will be more ferocious or not. through that again, you take that line of modeling, you will also predict the prevalence. But this now is more applicable in a given cohort. Thank you.
Maybe, I don't, but then I wanted also to add that probably we can also look at how we can incorporate the aspect of the one Professor Moridi was saying on machine learning. I don't know how moving forward, we can link the ODE with machine learning so that we can have a more predictive model. And then we can also think on, because malaria happens to be geographical. There are some places that are more affected, are more prone to malaria, and there are some places that malaria is not prone to. Maybe the use of GPS, so that we can get some sensors, and we develop some model that can actually assist in using spatiotemporal, I think, models to know us, to help us to even locate and model the possible outbreaks within a country like Kenya. But those are things that I'm thinking about. Maybe moving forward, we can look at, the student can also pick them up as we would also do research on this.
Okay, you know, yesterday I said, of course, that's why I was also challenging our students to get to the algorithms of the machine learning models, but you can only start from there when you understand the algorithm, then you know how to change it. Number two, I said that the geospatial models and the genomic models, currently the best models to work with them are AI models. Because once you have either the images or the parameters or the variables, put them into an AI model, a good one which is able to give a result, then from there, with that AI model, you're able to get approximately good approximation of the prevalence and the rest. Yeah. Thank you.
No.
Good.
So the quick one, at what point, thank you. At what point, as a data analyst, are you able to form your own parameters? Like you see where we stopped. We just indicated that these parameters are not functions of R, but something you developed. Of course, being a mathematician and doing this your area. What about any other data analyst who may not be at this field? At what point are they able to do this?
I don't know if I'm getting your question right. What I've said, remember, the SIR model is inbuilt in R. If you go to R, you find it, right? But it may not serve all of your purposes. So you may need to come up with your own model, and just by, I don't know how to put it right, but as a workshop like this one, you read more about this, and you are able to even to come up with your own model and validate it. Of course, there's some other aspect that it might require more of a mathematical understanding, but we are talking about the stability analysis and the rest, but you can do it to this level. You can develop your model before going to the analysis and the rest, but we can work together with you.
Thank you very much for that session, Dr. Congo. Maybe just before we clap for you, maybe I wanted to ask one. We need to know that even if you're modeling a disease, you cannot deal with all aspects. You only choose a particular portion, so you cannot deal with all aspects of a disease. That is why you must read widely before you start even developing the model to know what do you want to include and what do you want to include, so that you make the assumptions, and assumptions are made so that they limit you to a particular area. When it comes to the parameters, as is asking, it sometimes in working them out, we even use what we refer to as assumed parameters, so that you see what somebody else has done, you can take the average, and you use that parameter to be able to predict what you want to get from it. So you can't use all aspects. and you cannot all have to come with those parameters from the start. You use what is already there. You can do an average or an in between, an end or a start. So those are some of the things that you do when we are modeling. Modeling is a very wide area, and even when you're dealing with malaria, it can never be exhausted. Because you can see somebody else will do a vaccine, another person doesn't want to involve the vaccine, another person will decide even you want to do now, even after vaccination, what possibility is there, you know. So it's a very wide area as such. So this just tells us that we have a lot to do on modeling. And so we should organize much more in the future. So can we clap for Dr. Okongo, 5 factorial? Why do we use 5? I don't know, 5 is always, I've not heard anybody talk about 7 factorial, I always hear 5 factorial. So let's use 5 factorial to appreciate Dr. Okongo. So let us start. Okongo and the professor, utamalizia hiyo maneno, we want to appreciate Dr. Okongo with 5 factorial. So let us start. 1, 2, 3, 4. Thank you very much for that session. And we want to take a break for our lunch. And looking at this program, Okongo has actually covered development, simulation, and validation to a certain extent. There is only one area that we are going to miss out because we seem to be coming to an end. That is the session that we're supposed to have between 3:30 and 4:30 p.m. may not materialize. But we have covered much, and as you said, you don't, even when you're given food, you must finish everything. So you can't lazima to bakisha something. Where I grew up, if as a mother I make ugali and my children finish, I will not sleep. Yes, I will not sleep because it means they are not satisfied. So when something small remains, it is okay. So for even us, let us go that way. We will start from that point at another time. We will have our break for lunch. Then after lunch, we will have a small presentation by Swale. Swale, you give us a small presentation, 15 minutes. Then we have the evaluation of the training. There's going to be a tool. If you check your emails, there's going to be a tool for evaluating this training. So that is what we expect to do after Swale, and then we close the training or the workshop, and we call it the end of it all, and we meet again another time. So let us break for lunch. Somebody pray for lunch. This lady in the yellow, say something. Are you the one who prayed yesterday? Okay.
Let's pray. Heavenly Father, we give thanks for this session. We appreciate that you have given us time and energy as we break for lunch. Blessed in Jesus' name, we pray and believe. Amen.
We are going to assemble back at 2. Good afternoon. We want to start our final session this afternoon, which I hope is going to be very brief. We start with a small presentation. There is requested for about 20 minutes to do a presentation. Then after that, we will have an evaluation of this training. Please check your emails. There is a form for you to fill. Once you submit, we shall be able to project here and see what the results are. And that evaluation will be taken through by Dr. Edna. And after the evaluation, we will ask the chair of our department to close the function. Swale, take over.
Good afternoon, everyone.
Good afternoon.
I hope we are not that full that we need to call Professor Muma to give us teaching, etc. So my short presentation, it's actually, this is a model. Disclaimer is that this is not my research, it is someone else's research. Professor Neil Borg from US UCSF. And we had this presentation with him, and I thought it is best if we also do it. It's about, there are some aspects of modeling in it. So as you can see that the world's deadliest animal is actually mosquito, killing almost 725,000 per year. Then the second one, surprise, surprise, is us humans. So the aspect is about, we have talked about malaria a lot, but the aspect of vector, I thought that we have left it out, which is very important in malaria control. So why are these important? Because as you can see from the data that when you use insecticides, it is a contributor of around 68% of the cases which have been averted. One of the cases, I don't know if I can zoom, but it is Kenyan.
Just touch screen.
So one of it is Kenyan. Plasmodium normally takes 10 to 14 days to mature in a mosquito. So after 10 to 14 days, the mosquito becomes infectious. So we are safe to say that the older mosquitoes are the ones which are transmitting more malaria than the ones which are just born today or yesterday. So as you can see, this is the survival rate. The survival rate, so here it's 100%. Oh, now it is. Wow. So here it's at the peak when the mosquitoes are there. And then after some time, they die off. And then after 10 to 14 days, now they get the infection if they are bitten a human with malaria. So this is a model that has been done that, let's say, from all these mosquitoes, this is after 10 to 14 days. So at this stage, we took the mean of it, which is 12. It's when they become infectious. So as you can see, this is only, let's say we started with 4,963. They are potentially mosquitoes. potential infections, which is the 392 after this time, it's 8%. So normally, what we're getting from the mosquitoes, it is 8% of them, they are infectious with malaria, not 100, like many of us think. So the problem becomes is that one mosquito can bite around 10 human beings, or 20 human beings, transmitted it to many people. And what is another concern is that the mosquito which has the infection usually has a tendency of biting more than the ones which do not have infection. So this was the intervention that has been done. So it reduced the survival rate from 80% to 65%. So when this happened, the percentage reduced from 8% to 0.8%, which is almost no malaria. And this is, remember, is just reducing by the 15% of the mosquito population. So by reducing 15% of the mosquito population, you have reduced this 392 to almost 25 mosquitoes. And you can do it further, and maybe let's do interventions. The interventions have covered and killed almost 50% of the population of the mosquitoes. So imagine we're even reducing it further to 0.05% of infectious mosquitoes. So vector control is an essential part of controlling malaria in Africa and in Kenya. So let's say that you use larvicide. So larvicides are not very effective in controlling malaria. Why is that so? Because even if you use larvicide, the mosquitoes that can infect malaria, which are the older ones, they are still there at 7.9%. You are just killing the young ones, and they're just going to have a way and lay another eggs tomorrow. So the most effective part is, from this study, is that it is better to use survival rate, because as you can see, the adults have a survival rate at 80 still. But the larvicide has reduced by 50%, but still the infectious mosquitoes are still at 7.9%. And here is the showing. So let's say we are at the same number, 4,963 infectious mosquitoes, and which is the survival rate is 80%. So the potentially infectious, they will still be 7.9. And the larvicidal is still the same. Remember, it is 196, but it's still 7.9. So let me show you what happens when you do the interventions. So when you do the adult interventions, as the larvicidal rate, it's still there. The adult intervention, just by reducing it to 65%, you can see it's 0.8, or comparing it to the larvicidal one. So I think I misplaced it, but I can just explain. So comparing to the larvicidal, which are going to be used, they are going to kill the larvae and the eggs, but still, the population is still infectious at 7.9. So while doing your interventions, it is essential to find the gaps that are there and study the behavior of the mosquitoes, and then do the interventions that are going to cover up on both sides. So here it is what I mean. There are 3 types of species of mosquitoes that infect malaria. So there are some infections, such as the species 1. The species 1 feeds outside most of the time. It doesn't go inside the house. So the moment you're going to use mosquito nets and IRS, it's not going to harm them in any way. Why? Because they bite outside. And the second species bites both outside and inside. And the third species bites only outside. So while having interventions outside, the third species which bites inside, it has no impact in those types of mosquitoes. So while you are designing your study, it is essential, it is very important that you understand that these mosquitoes, you need to understand what is the behavior of the mosquitoes that are around that area. What is the biting time of those mosquitoes? And at what time are people mostly at risk? For example, there are some mosquitoes which bite outside at night. And some people, maybe in that area, most of the people are asleep inside the houses. So you doing interventions outside the house, it has no impact because no one is outside. So you need to understand what interventions that you're going to do and where you're going to do it. So these are the examples of the interventions that are being done. There is LLIN, this is treated bed nets, and there is IRS, which they usually do it in the walls. And sometimes it's that these mosquitoes can also be resistant to this, to 1 or 2 interventions. So you need to understand, are the mosquitoes in that area resistant to that, so that you can apply the most appropriate intervention. So as you can see, when you apply the mosquito bed nets or IRS, it's going to have an impact on the first or the third species a lot. It's going to eliminate it. If assuming that they are susceptible to the medication that has been used in the IRS and IIN, and also some of the species 2, because some of the species 2 will be outside, assuming that they will be safe, but it has no impact on species 1. So it is important to understand that what are the local vector species. For example, there are different species. For example, Anopheles gambiae usually bites people inside the houses, but Arabiensis usually bites animals outside. So if you're getting bitten outside, it is most likely that it is Arabiensis if there are no animals around. So there are some scientists suggesting that if the area has a lot of Arabiensis, then it is wise for you to keep animals so that they can go after the animals, because they love the animals more than humans, rather than just living without. So as you can see, it is that these species behaviors and compositions, they can determine what is the efficacy of the sampling method. What method are you using? When and where is malaria happening? What is the potential of an intervention to work in that area? If you understand this, you can help in not using a lot of resources in an intervention that's not going to work. And we can also see what is the intervention, effectiveness of the interventions that have been applied. So this is what we want. We as scientists, we as moderators, we need to be here. You can see that there are some parts. So let's say these are the interventions that has been done. Let's say these are the interventions that have been done. So this is the human behavior, the vector behavior, and there is intervention A, which has been done. We need to understand what is the protection that we're getting from this. What are the gaps? We need to understand what are the gaps that are there, and what are the best interventions that can be applied in that area, so that we can cover this part of the gap, so that we can have complete protection. So I love vectors a lot, and this is why vector and entomological surveillance is important. You will understand what are the drivers of the transmission. What is the potential of the intervention that has been applied? What are the potential of it being working? Or if you're already having an intervention, how well is that intervention working? It can also help you to optimize the intervention. E.g., when you go, for example, this professor, once he explained that he went to a village and he was busy collecting samples outside, and he's getting a lot of samples of vector. But then he wondered that I'm outside, but at this moment there is no one outside for the whole week. So he started to ask, how do you people live? And he realized that the intervention that he's doing outside is not helping anyone. Because probably the mosquitoes that are transmitting malaria, they are already inside the houses, while he's doing intervention outside at night. So it helps you to optimize the interventions, and also you understand how is it not working, why is it not working. And this mosquitoes resistant. The only way you can understand that it's by doing vector surveillance, and maybe you look at the genes of resistance instead of the mosquito. And also you can monitor changes. Are there any changes? Let's say now and after five, let's say now and after, let's say around 2 months. Are there any changes that has been happening? And my big concern to us, and this is one of the saying of another professor, just to end my presentation. Yes, so this is what's happened. So this Professor Jose Najera, who is a former WHO epidemiologist, stated that before DDT, malariologists were trained to be problem solvers. So most of us up to date in Kenya, we are still problem solvers. But after DDT, that it caused a lot of harm, then malariologists were trained to be solution implementers. So I want us to ask ourselves, are we problem solvers or solution implementers? Thank you. Is there any question?
Any comment?
Thank you. Thank you, Swahili, for that presentation. I want to refer your attention to a finding we established some years ago with colleagues of mine when we were working in Isipe in Nairobi. We sought to find out why two things. Why is it that when people are sleeping, mosquitoes would want to bite around the ear? And we also sought to find out why is there. So we came up with the two reasons, and we found this, that we published a paper to this, that CO2, carbon dioxide, is a very good attractant for the mosquito. Number two, that the human ear produces about 300 compounds that are very good attractants to the mosquito. Actually, we were able to do ear swabs and analyze that through a GCMS. And it detected a number, actually a total of 300 chemical compounds produced by the human ear that are attractants to the mosquito. Can this or has this been exploited for vector control now that you are in vector control?
Thank you so much. That's a very good, interesting question. So there are some different parts. There are some different vector collection methods. And if I had time, I would have also done a presentation of that I have. So, but we can arrange it for next time. So one of them is human bait. Human bait, using a human as a bait. So what you do is you keep a human inside a protective net, and then you have another net around that person. Then when the mosquito hears that carbon dioxide, because they are attracted to carbon dioxide, so they can be attracted to that carbon dioxide and that human, and then they come inside the net. Remember that the outside net is being treated. It's treated. And after some time, the entomologist or the person who is doing the vector work comes in and sprays around the net. So those mosquitoes, probably they will try to bite that human. They cannot get to him. So they will end up hanging on the outside net, not the inside net. And it will be easy way to cut it. Also another way, it's the use of dry ice. Dry ice is CO2 in nature. It sublimes to air. So we usually use CO2, the dry ice, to attract mosquitoes. So there are many techniques actually which are there and which are being used. But I cannot explain all of them now because due to time, but I hope to answer the question.
Maybe on that, mine is YouTube. We all read these YouTube issues. And I keep seeing that mosquitoes, they like biting people with blood group, particular blood group. What's this? There was one who was saying AB, another one I read
Okay, most of the mosquitoes love biting people with the other, they do not like O negative. That's the blood group which they usually don't go for. Why is that so? Because remember that when they bite the other blood groups, they usually, what we hear A, B, and the resters, it's normally another antigens which are outside, which are protein in nature. So they are going to get more benefits when they go to fight someone with A, B, A positive.
What would have made our mosquito know that we're
I'm not sure to answer that.
That should be the science. So that will be something to look at.
But most probably, maybe, I can just say this from my own assumption, but I don't know. Maybe it's because once they bite once, they understand they need to shift from value.
Another reason could be that people with A negative produce a certain odor compared to people who are not, because there must be a signal to connect the mosquito to the house. So I would also imagine it's about the weekend. Some kind of
Eight people per day or during their lifetime. Because once the mosquito bites, it takes a blood visit. But before biting another, the mosquito will
this in the, what is the term? No, before when you are putting a mosquito, before you invite the other person and say that in that way, that blood, the mode of transmitting the pathogen.
There is usually a cycle inside the mosquito that goes on until it ends at where the parasites and the virus land from the mosquito now ready for injection to the next person. So there is also a cycle inside the mosquito.
So before, so the point is to inject the blood to you before by taking your blood.
So I can answer that. I think the first thing that you need to know is that not all the mosquitoes transmit malaria. And even due to the species of Anopheles, not all Anopheles transmit malaria. It is the female Anopheles which can be able to transmit malaria. So what happens, the parasite has a asexual and sexual reproduction. The asexual reproduction usually happens in humans, and the sexual usually happens in the fly. So what happens in the fly? First, the parasites go to the midgut, and then after midgut, that's when they go to the salivary glands of the mosquito. And that's what we are saying, it takes around 10 to 14 days for that to be established from the vibe of the taking the parasites into its body. So that period, we are not going to say that it's not going to lay eggs. It is, but it is not vertical. It does not transmit that malaria to the eggs. It's going straight to the salivary gland. So I don't know if your question is answered.
Okay.
I don't know how I got this question because I think the time that idea the mosquito, once it bites somebody, it cannot bite again. That's what you want to say. How many people can bite?
I heard that you talked of 8 people.
Okay. That was just an assumption.
Okay.
That I'm just giving an example that, for example, a mosquito will bite 8 people a day because it does not bite once. Most of the time you realize it, you want to chase it, it runs away. It goes and bites again. So the assumption that, let's say a normal uninfected mosquito bites 8 times a day, then those infected, there are studies showing that they have a tendency of biting more. So they bite more. The parasite inside them makes them want to bite more. And whatever they use, those mosquitoes usually take that blood meal. They only meet once in the whole of their life. The female ones meet only once. They have a special device inside their body, it's called spermatheca. So the spermatheca stores the sperm once they met with a man. So once they have that, then they release that slowly during their lifetime. They don't need to have another mate. So as you can understand that the blood meal now helps in the oviposition of the eggs. That's where the blood meal comes, but they don't feed it for their own. They usually like fruits for their own.
So maybe to appreciate Solen again, let's appreciate Solen. 3 factorial. So 3 factorial. Thank you very much. And unless somebody has anything else to add or to say, we want to call upon Edna. I'm assuming that everybody you have filled the evaluation form so that you have after you submit, you can see the results.
something or say something to save myself from attending to each one of you. People asking how to join AMNET, please take 1 minute if you are on the internet and go to Google. This will take a minute. Just go to Google. If you're on the internet, are we on Google? Google? Google. Type in Global AMNET. Type in Global AMNET. Type in Global AMNET. We are there, isn't it? It opens a Google list. There is AMNET, a global community of malaria modelers. Click on that. AMNET, a global community of malaria modelers. We have clicked, isn't it? Anyone there?
Is it what
We said Google.
You demonstrate?
Google Global AMNET. Connect my search on Google. Global AMNET. It should open a page that starts with the AMNET, a global community of malaria modelers. Are we there? We are there? So can you click on that? AMNET, a global community of malaria modelers. It brings a page of AMNET. Simple. Okay? If you scroll down that page, you see join, and then they have highlighted a form where you can join. I hope we have all gotten there. And if you have not made one or two persons seated next to you and done that, but still if you are completely unable after the meeting, I can briefly take you through so that we allow the Canaranis continue with it. I'm sure.
Anybody has any problems or any kind of question? You want them to know? Yeah. Just come with a document.
Yes.
So then I just work with that. Let's take your computer there so that we're able to see. Oh, it is there. You can use that one.
Someone, yeah. So you go to global community. Click. Scroll down. There is a form to join. Yes, click on the form. So that is the form you fill, but go back a bit. Go to the dashboard app. And you go to opportunities, you go to funding. Yes. So immediately you join, you can go down and apply for those two grants. But I would advise that if you are doing a first application, you can choose the small event grant. There have been so many unfinished businesses in this workshop today that it will be funded by a small event grant. People like Dr. Kongo now and Professor Murithi can now try the large event grant. We are saying $40,000 because on top of the $4,000, they give you extra $4,000 to administer the grant. So in total, if you win the large event grant, it is indicated 40, but you will be given 44,000. That's all I wanted to say.
Thank you very much, Emma. We had earlier even shared this form, and if you did find the link, you can scan the code, and meanwhile we'll be looking at the results from your feedback based on the workshop. So I think Site will give us the
Okay, I think you can start from the first one. So we asked, the question was the course well organized, and your response was 26% said agreed, and 74% said strongly agreed. So for the organization of the course, 74% agreed that it was strongly or it was well organized. So let's move to the next question. So the next question was the number of participants appropriate for such a training? And 37% said they agree, and 63% said they strongly agree. So it means that the participants strongly agreed that the number of participants was appropriate for such a training. Let's move to the next question. So the next question we asked was that the training included the right amount of technical components, and actually 84% said they strongly agree. Let's move to the next question. The other question was the training had enough practical components, and 74% said they strongly agree with that. Let's move to the next question. The content of the course met my expectation. 53% say they strongly agree, 9% they say they agree. So all of us agree that the course content met their expectation. Let's move to the next question. Was the course engaging? And 79% say they agree that the course was engaging, or they strongly agree with that. The next question. The question was the course easy to follow and understand? And 58% say they agree, and 32% say they strongly agree. So a big percentage actually agreed that the course was easy to follow and understand. Let's go to the next question. Which session of the course did you find most challenging, and why? So I think we'll look at the green one, what the green one says, the formulation and simulation of compartment models. I think that is what Daktari was trying to explain to somebody like me as well, was trying to understand or what was going on. So probably you can take us through another workshop for those of us who do not get to understand the technicalities of I feel confident enough to apply what I have learned in this course to my day-to-day job for end-on studies. And 47% say they strongly agree, and 37% say they agree, and what percent is 7? I'm not sure. 5% say they disagree. The course facilitates an environment that enables networking and interaction, collaboration beyond the course, and 63% say they strongly agree, 37%. So all of us actually agreed that this facilitated an environment for collaboration. Would you consider, or what would you consider to be true of the most relevant aspects then we make more people aware about such training, proper understanding of dynamics of disease, so that one can be able to develop a useful model about learning, spatial modeling, more detailed training for data analytics using R, and a number of aspects that other comments, so these are the comments that participants gave for the workshop and the interactive section. They need for a follow-up for mastery. I think then probably really going to give us a way forward. And then we should support stronger collaboration and lead now at least when you get out of here, go with a contact of one person that you intend to collaborate in the future. The training has been very interactive one and well done, and also shared recordings with the participants. Any other question? I think that is the end of the questions. Otherwise, thank you for the organizers, thank you for the participants for being good participants of this workshop.
and where I'm he failed. Because he failed to know that there is a lot chemistry and we are a good scientist and a researcher. Don't love yourself so much. Don't praise so much yourself. You can see, you might come out with a good idea. Ameambia mimi kutengeneza. Alafu mimi ninaenda kusema ni mimi. And next time that analysis will continue this way. Because I'm having a practical example where we were invited to the many people who are supposed to rent the ground and I realized unless we modify this, we are not going to get this. Then they brought in another university from city which I don't want to mention. Then we went and walked the because, you know, I like going as a researcher. I was going to do some modeling and from young, you know, I felt them, they are very strong. So I came across a version who was painting real data. Not from, you know, those are not real data. I wanted them to use real data and over experience. In another word, it is important not to spend a lot of your time, you know, even a private person can communicate being happy, being the time when you are you are not thinking. But I wanted you to if God willing, when we start becoming happier, you should be trained on a model which you have come up with. I'm not talking of a model which you change only one parameter. Look, this is a model which you can code, which is mine, and you compare with it. So I wanted men and women who can promise us what duration can we give ourselves at least many allegations about let's say have come up with the this is just playing with numbers. Who can promise us, and we reflect with God willing, and compare our best that we will keep us the next time we are having that's what I believe. I don't want even to see what I'm your model. And to come up with model, you need to integrate with us. Really, and you cannot do anything without model. Pretend to go, when you go, I guess, some of us are doing it to speak. You are very good after our work in the student. Right now, you are speaking and I get it because of the inner channel. This is a thing done all problems. Next time, whoever is coming to present, please, I would like to properly. So that even if you want to attack this town, you must do exactly what you are doing. That instead of going to this versus there, it is better as an advantage, and it is an advantage, and it can still be done. I know that even now what and I tell them this is the thing, and we are this, and remember. And after that, it's supposed to be taken to work. And remember, who will be the and